Hello community! We have today a multi-agent, and because AI is so boring, let's do a topology DSPy, no? And you might say, hey, I know everything about multi-agent, no? If I ask ChatGPT, hey, what are the multi-agent frameworks that are well known and commercially available? You have Crew AI, you have AutoGen, you have LangChain, you have Microsoft Semantic Kernel. And if you're really into the research edge here, you see I have here multi-agent code explained here by OpenAI, or their multi-agent fine-tuning, MIT, Harvard, Stanford, and DeepMind. And then we have a complete playlist here, multi-agent code. And the latest here, just 3 weeks ago, if you code with Anthropic, Pydantic, together, AI, multi-AI agent configuration, and you would say, everything is here. What do you want? Well, let's look at my last video where we talked about OpenAI and deep research, that was for science. And remember that we had a little bit of a problem here, especially here in the TDC reasoning part, where we looked here and we discovered here, there must be something wrong with the process reward model, yeah? And now imagine this is just one agent. And now with this single agent complexity decision making, we now move on to an interlinked multi-agent complexity. Would this be something for a topic? Would you be interested? Yes, then hey, this is the video for you. So let's open this video up. And you might say, okay, humans are not able to do this anymore. So here I had a video, AI agent that designed themselves. And remember, the framework was ADAS. Now, this was here the beautiful paper, August 2024. And this was simply automated design of agentic systems. So multi-agent system that automatically design themselves. And you would say, perfect, this is it. No, this is now the best system. No, unfortunately not. Because you remember we also had here this self-consistency in our agent, this self-refining. And here we had our DPaid multi-agent structure and everything together. And yes, it is a beautiful GitHub repo where we had automated design of agentic system. Here was an outstanding paper. Everything was great. And these three contributors here, amazing work. But you know what? Now we need a spark. We need a spark of genius because we go the next step. So imagine we could define the complete multidimensional, multi-agent, multi-complexity system simply as a single mathematical optimization problem. Now, it's easy to define this problem. It's another topic to solve this problem. But we say, hey, give them a search space A that defines all valid configurations A over a block of multiple agent. We can now define a workflow topology optimization problem that can be expressed as the following optimization problem with an objective function f, and on a target input and an output set D. And this is simply here the optimization problem that we have to solve. And this is it. Nothing else to it. Couldn't be simpler, no? Welcome to the new system. Multi-agent system search. So now we do exactly this. We search here in a solution space here for an optimization problem. So it's a simple mathematical problem, but you know what? Because we want to have a little bit fun today, in this video, I will not show you any mathematical formula, but I will explain it completely here without mathematics, because you know, it is simple to understand. So what do we want? We want to go the next step. And I told you all the other system and everything up until now, it was beautiful here, the optimization of the workflow topology. And now with this new MAS, the multi-agent system search optimization, we now integrate here on a different level prompt optimization. And prompt optimization for agent, for block of agents, and for arbitrary configuration of agents in a topology. And you see, now mathematics would start to make so much more fun. But you know, it's also a challenge here to explain this in a simple way. So let's start. As I told you, MAS is simple here, if you want to be a little bit more specific, a local to global optimization paradigm, no? It simply ensures that the individual building blocks, these are single agent, multi-agent configuration in a particular way, they are robustly optimized and then orchestrated them into an effective overall system. This is all that there is to an optimization paradigm. But now how to code this is a much more interesting question. Especially if we go now on different level of the complexity of our topology. So in the easiest way I can think of, topology refers here to the structural arrangement of our agents. and the particular workflow between those agents in their specific arrangement. And this kind of dictates here the sequence of all the interactions they have. So, different topology, parallel aggregation, serial reflection, or a DSPy structure, all of these represent different strategies for combining here the capability of our multi-agent system. And now, you understand immediately now, we have to choose not the right topology, the right configuration of the structural arrangement of our multiple agents. This is now critical to be successful. So let's come to the core idea, and this is simple. We go now here in a 3-step algorithm in our multi-agent system search. Let's start what we know and let's see how we can improve our standard classical old knowledge. So here we go, and we have here the performance of a particular Gemini 1.5, never mind about it, in 2 benchmark. This is a question and answer benchmark, and on the right hand side you see here a coding benchmark. Never mind. What I want to show you here, we have here a chain of thought as a base model, and now if we go here with different methodologies, and I just showed you these 3 here, reference and the debate multi-stage, multi-agent stage, if we apply this, you see the performance differs maybe 1% or absolutely 0 or plus 3%, or even if you have a summarization, minus 2% in the performance indicator. So you see, whatever we do, whatever is our particular task, it is really sensitive here to the query, to the user query. So we cannot find a general solution. We have to adapt our solution. Because as you see here, plus 7%, minus 15%, if you have a self-refine implementation. And you might think, hey, if an agent is self-refining itself, no, it must increase. No, as you can see, it has a negative effect. So we have to find a configuration where, for example, this self-refinement is either not at all present or is present in a combination that will increase the performance. So we see there is now a real sensitivity to the configuration. And now look at this. Again, we have the accuracy of a system, Gemini, whatever, and we have here the number of tokens. It's a logarithmic scale, and you see here now for here the self-consistence here. This is our curve, so we go from, I don't know, 73% to maximum 78%. Even with a lot of tokens, here the total token count for the prompt optimized agent here per question, and we have here the mathematical data set at Gemini 1.5 Pro, and we compare this now. And then the debate, multi-agent debate, you see here in the yellow. Yeah, it's a little bit better, but it's real close here to the maximum performance. And then we go with the self-reflect here. This is now the best. We have here a plateau. And again, we are somewhere at 78, 79% accuracy. But you know what? Now they found, hey, if I start at first to go with a prompting optimization, and then I take care about the configuration of my agents. So at first, if you want, I have a single agent internal prompt optimization, and then I start here with the configuration of them. Look at them. Immediately I go from 73% to, I don't know, 79%, and then, yes, it increases. So this is the beautiful aha moment where they said, okay, so first step seems to be optimize here the prompt structure itself. So let's do this. And you might say, hey, we go with prompt engineering. Of course not. Hey, prompt engineering is so 2024. We go now with automatic prompt optimization techniques that are really, really advanced and beautiful. So you have here now the schema of our new MOS. So we have first step, the prompt optimization space. We have to find here the best and perfect instruction and the best here exemplar for this. Then if we have this for one, or maybe we have a single agent benchmark, a reference level, then we will start to configure multiple agents in different designs. We will have a look at an aggregate function, at a reflect function, at a debate functionality, summarize. We have tool use, like a Python, for example, or whatever, a database. And we have customs like summarization or whatever. It's already there. So whatever you like. So the second step would be here the topology optimizer, how we can put these things together And by the way, what is the maximum number of agents or the least number of agents to perform the job with the best performance? And then I bring everything together. I have now different topologies that I can test out. And now I have here together the prompt optimization for the optimized topology of those agents. And then I just optimize my prompt. So you see, we are in a 3-step optimization. So we are still in the complete mathematical optimization, that I told you at the beginning of this video. At first we have a prompt optimization space, then we have a topology optimizer, and now we have an optimized prompt for each agent type in a particular optimized topology. Beautiful. So we just need to calculate this. Now, interestingly, Google said, hey, we built some blocks. No, it's much more interesting. So we have a predictor. This is our base agent. This is our reference agent, if you want. And if we want to aggregate here knowledge information output here, we have here an aggregator agent. The self-reflect agent, again, we have a predictor. And then we have here a reflecting agent. And beautiful. And then we have a summarization. So we have long input. We have a summarization agent that gives on down to the predictor agent. Beautiful. Or if you have multiple agents that debate with each other, we have then here the debate going on and tool use, and I think it's clear. So what we conduct is here a block level prompt optimization for each agentic module individually. So for each of those module 1, 2, 3, 4, 5, we have here a prompt optimization in a reference to our baseline optimization by the predictor. So we have, if you want, numeric values that tell us immediately for our optimization procedure, hey, this is good, this is better, try a different topology, try a different configuration, beautifully. As I told you, the second step here is the topology optimization itself. Here, imagine, we have a linear chain of agents, and this gives us here, just as a demo, 63% performance. But if we build here this not as a linear change, but here as an interlinked configuration, we can achieve 75% with the same input-output data, with the same prompt structure. We just change the topology, how we arrange the input-output structure here of our agents. And if we have found the best topology, let's say this is it, or this is it, whatever, we then can do another final prompt optimization now that we have the final topology. You see, 3-step optimization process. Couldn't be easier, no? So just to summarize, if you want to see this more in a written down form, this is for you here. So we have kind of a set of influential topology that we work with, that Google works here with. Aggregate, this is agents collaborate in parallel with diversified prediction, which is then followed by an aggregator operator that obtains here the most consistent prediction. And the aggregate block can be parameterized by n times a agent acting in parallel. You have either a majority vote or self-consistent, and it sits with this topology. Reflect, agent can act as verifiers, providing critiques and improvement suggestion based on the former prediction. So the feedback is then fed into the predictor, the reflect itself, for an iterative improvement. Similarly, reflect can be parameterized, or the debate agent just debate, and this topology would evolve here a mixture of agents, and we have the number of rounds of debating. So let's say we have 3 agent debating, and we go 3 times a merry-go-round. Or you can combine them in different ways. So if we go now here with some, let's say 5 topology building blocks. Now, we can hypothesize that manually crafted topology might be not optimal for your particular task. But you know what? We have a mathematical optimization problem. So if we have an automatic topology optimization, this is just perfect, because this will design here the search space and the search configuration for multi-agent system for us. We don't have to care about this. We just need here the code that the system is self-optimizing, self-building. So we have here the best topology, and then it does here the overall, if you want, prompt optimization for the new, more complex agent topology in total. Again, step 1, 2, 3. Let's have a look again at step 1, the block level prompt optimization. Ensure that each single agent is optimally configured. We do this with an automation. We do this with a state-of-the-art prompt optimizer. We use here MyPro, and yep, starts up. We have our pre-data with a single agent APO, and we can measure this. And we have here the agent type like a predictor, reflector, summarizer, or a debater. Great. If you want to learn more about MyPro version 2, here, this is the page for you. We're here at Stanford University. This is, of course, here within the framework of DSPy, and the multi-prompt instruction proposal optimizer version 2 is already, as I just noted, as you see here, out of date because we get a new base DSPy 2.5 plus, hopefully soon. So this would be great, but never mind, you can work with MyPro version 2. And if you are interested here in the roadmap of DSPy 2.5 plus here, you see there, MyPro 2 was introduced in July 2024, so already more than half a year old, my goodness. And they're looking here for the next iteration, for the next improvement. Maybe it is within, I don't know, DSPy 3, no idea. But so if you're interested, this is the page for you. Or if you say, okay, beautiful, I have a video for you where I explain here DSPy, the self-improving machine learning system, and the next generation. We call it text grad. This is an automatic differentiation via text. Both are from Stanford University, so both are beautiful, but you can stay with DSPy. Never mind, this works just beautifully. And if you want to take the step to the next evolution, just use text grad. Step 2 here from math is now, the workflow topology optimization problem. So we have here our set of topologies, the aggregate, the reflect, the debate, the summarize, and the tool use. And now we are just measuring here for each particular topology the performance gain when integrating this particular topology configuration over the base agent. We just use a softmax function to determine here the selection probability for each topology dimension. And yes, we have rejection sampling here, but this is more or less a known process. What you need is just a compute infrastructure and maybe quite some money. Okay, step 3, now the final step in our optimization, the workflow level prompt optimization of the complete complex topology interdependence of prompts. So not, careful, it's not the independence of the prompt, but it is the interdependence of all the prompts in all the specific configuration here in the topology, and we just optimize here the prompt for the agent within the best found topology possible. And again, you can use the same MyPro prompt optimizer now to fine-tune the prompt for each agent here in this selected best, more complex topology. But there are also other prompt optimizers you can use, so you're not bound here to this particular optimizer. If you want to see this here now on a quantitative level, you say, hey, what is the strength? What is the effect of each of those 3 steps? Here we have a beautiful one. And this is done by Google, and they show us here the prompt optimization on the block level gives us a jump from 62% to 79%. This is huge. This is the most dominant factor we have at all in this system. Because, look, the workflow topology optimization, so how you configure here the setup of your multiple agent just is a jump from 79 to 83. And for the third step, the prompt optimization of the complete system is even minor, just 83 to 85%. So if you do here the block level prompt optimization, you get, let's say, 80% of the effect already. And then, you can go here for perfection. I think this insight is absolutely amazing. We have now achieved that a multi-AI agent system is built in an automated way by, if you want, multiple AI systems that configure themselves, optimize themselves, calculate here possible new configuration in a configuration space, and you can even define custom agent for a particular task or for particular tool use if you have computer simulation for particle accelerators or astrophysics or chemistry or medical or whatever. So you can build this and then the system optimizes itself. if you want to see this, so what is now the result of this optimal configuration? How does it look like? So here we have all the different tasks that Google examined. And as you can see, for mathematical reasoning or for discrete reasoning, or for here you have 3 for long context understanding, or here 3 coding tests. We have validation, test data set size, and then we have here the topology search base. So you see, normally summarize, aggregate, reflect, debate, or aggregate, reflect, debate, and the executor. But now, as you see in the mass system, we apply them in different runs, different iterations. For example, here for the mathematical reasoning, they found that if they have the structure in the block of aggregate, reflect, and debate, if they run this 9 times, they have the best result. Okay, so you see, as easy as this. So here you have again for each task, mat, drop here, now you have the task here. You see this is now the, if you want, the best, perfect is maybe a little bit too strong. This is the multi-agent topology that is successful in the task. And as I told you here 9 times, you see this exactly here for the mat. Here you have the predictor. And if you run this configuration 9 times, then you should have here the best multi-agent topology available for this particular job, for this particular data set. You see here for human evaluation, it's a different one. For live code bench, it's a complete different one. You have 3 aggregate functions here, 1, 2, 3. Then reflect, you have only one R. For the debate, only one, and execution, only 1. So interesting, but this takes time to compute. So the more complex your task, the more time you need to invest here in just hardware infrastructure. This is here the beautiful publication, February 4th, 2025 by Google and University of Cambridge. Sorry, almost forgot University of Cambridge. Those are the beautiful authors, and they give us this paper about the latest in multi-agent design, optimizing the agent with better prompts and, let's say, new technology. This is the mass system. Now there's one particular point I would like to draw your attention. It seems so easy, no? But have you noticed that there's one element missing? And I mentioned it at the beginning of the video, and this is the reference base. I told you that we have a baseline agent, we call this the predictor agent. And at first, before we start, this is the cold start here of the complete reasoning engine that we do here of all the agents. We take a predictor, a baseline agent, and optimize the prompt first. So you get a measure of how well a single, simple agent in no configuration at all can perform the task. If you think about it, this baseline is crucial for all the later optimization because you have to optimize in reference to a baseline performance. So whenever you introduce now more complex agent or more complex topology, you need to know if they're truly improving this simple baseline agent, because I've shown you, you can also have a negative performance, a minus 12% drop in the performance. So this predictor is really important. Now, you could theoretically say, hey, I optimize my prompt for all the agent type and all the topologies simultaneously. But at first, given the complexity of your job, it would be incredible complexity as a whole, and it would be extreme computationally expensive. So this single warm-up predictor stage is a way to break down the complexity, and you have not the best, but a real good benchmark. You can think about this essentially as a preconditioning here, the prompt search space. It's like finding a good starting point here in a vast search landscape. And after the stage 1, after warming up with the predictor here, then mass optimizes the prompts for the other agent types, you know, the reflector, the debater, exactly. And to measure now the influence of each of these new agent types, they compare the performance of the system to what the new agent type is to a system without it, and this is the warm-up predictor. So you see this predictor performance becomes the reference points for evaluating here the added value of each new agent type and each new agent complexity. I want to show you now the prompt structure because, of course, in DSPy here we have prompt templates that we start with. We use here this in the mass search base, and for each type of agent they found here different optimized prompt templates. Now for mathematics, the task that I showed you at the end of DSPy, this is it. It is rather simple. Let's look at it. We start with our predictor, the simple let's think step by step. This is our chain of thought. So we have a question, then we have the reasoning, let's think step by step in order to produce the answer. Then comes the reflector. The reflector simply says, please review the answer above and criticize on where might be wrong. If you're absolutely sure it is correct, output true in correctness. So what you have your question, you have your text, you have your reasoning with the step by step, and then you have a feedback and the correctness. And whenever now the LLM decides here in the correctness that this accuracy is good enough and it gives you a true, this would be here that now we found a solution and the system stops. If not, if you have a false flag, then we go to the refiner. The refiner says, hey, given your previous attempts and all the feedback we received, carefully consider where you could go wrong in your latest attempts. Using insights from your previous attempts, you learn, try to solve the task better. Show your final answer bracketed between answer and stop answer at the end. So now you have the question, all the previous answers, the reflection, the correctness label, the thinking that went on and through, and now the answer. And then we have the debater. Well, these are the solutions to the question from other agents. Examine the solution from other agents in your rational. Finish by giving an updated answer. Show your final answer bracketed between answers and end of answer at the end. And you see, this is here for the math benchmark where DSPy at the end. Google showed us this is here their prompt template that they used. Let's go here for human evaluation. Maybe this is a little bit more interesting, but it kind of is really similar because we have the predictor. Let's think step by step. So you have the question, then you have all the thinking and an answer. Then we have the reflector. Please determine the correctness of the solution in passing all test cases. If it fails, based on the error message you received, this is here coding, and the trackback, think step by step, carefully propose an updated solution in your answer output with a correct code implementation in Python and a debater, and you get the idea. So you think it is rather easy? We have here the beautiful tool of DSPy here for an optimization here of our prompt structures on different levels. And all of this is measured against our baselines. And just as a reminder, the simplest baseline you can think of is a chain of thought. No? Then we have this SC, this self-consistency, maybe a rule-based majority vote. Then this self-refinement, where if, as I showed you, a stop criterion could be when the self-reflector outputs here a correct in the prediction or a true in the prediction. And then we have a multi-agent debate, where you have multiple agents. Let's say 3 agent is a good source here. And you let 3 agent debate for 3 rounds on simpler mathematical problems. For more advanced complexities, 12 rounds I found quite helpful. So there you have it. We have a brand new idea by Google. Beautiful. And they tell us here, all the ablation studies clearly show that the block level prompt optimization, so stage 1, step 1, contributes here the most significant portion of the performance gain. As I showed you, you make a significant jumps. And they say this highlights here the crucial role of a well-designed prompt for individual agents, confirming here the paper hypothesis that this is important, especially here in multi-agent systems, and simply scaling the number of agents or focus only on the topology without optimizing the prompt, this would be a mistake because this is less effective. Therefore, the performance variation across all the different topologies tell us, hey, we have to use an automation for the optimization here. So we not go only for the topology selection, but also here for the prompt selection. And MAS, this new methodology, effectively identifies and leverages these influential topologies. So there you have it, a multi-agent, but now a complete automated system for multiple agent. So with the least amount of agent, you should be able to solve the given query. And we use here the DSPy optimization, not only here on a single prompt in a single agent, but we optimize single agent, we optimize for topology DSPy, and then in the third step, again, we go back here and do for a given configuration of multiple agents, we do again a prompt optimization with DSPy. Maybe whenever you see this video, we have a new version of DSPy, or you go with your text grad optimization. Whatever solution you choose here for your optimization problem, you see AI is absolutely fascinating. And all the new ideas that come out daily, my goodness, it is great. And if you want to subscribe to this channel, this would be great, because in the moment I don't know what will be my next video, but as a subscriber you will be notified immediately.